All right, guys. So today, let's talk about this Unit 2 test review number 1. So what we're going to start with is we are going to start with first question, Venn diagram. We are trying to figure out how to, well, just answer probabilities in this situation. The diagram's already done for us. So I just want to work on finding the probabilities. If I can get my screen to scroll, y'all, sorry. If I can get this to work. Switch pens. There we go. All right. So what is the probability that a student is a Facebook user? Now remember, I'm just asking about Facebook user. That's a total. So Facebook user is a total circle. So I'm going to take that 93 and I'm going to add it to 34 to end up with, let me pull out my calculator so we have accurate information, is 127. Now it's 127 Facebook users. How many people are there total? Doesn't tell us yet. So I guess we need the total for the whole diagram. So the total for the whole diagram is 150. So of 150 people, so it's 127 out of 150 for the probability of a Facebook user. This has it in decimals, so I'm going to use my calculator. The closest we have is 0.85. So what's the probability that a student is not a Twitter user? Okay, so not Twitter. Not Twitter means the numbers that are not in Twitter circle. So the numbers that are not in the Twitter circle are 93 and 15. So 93 plus 15 is 108 over 150. Again, we've got this as a decimal. So 0.72 is my answer. What is the probability that a student is a Facebook user but not a Twitter user? Now this gives me two classifications. We have Facebook. We already know Facebook is a circle, but not Twitter. So it's not just a full circle. This is part of a circle. So Facebook but not Twitter is 93 out of the total 150 because, right, we're talking about everyone out there. You can leave it as 93 divided by 150, although that does reduce as a fraction. You have 31 over 50. I believe that is 0.62 if you want to put it as a decimal. Remember, we're okay with either fractions or decimals as our answers. We do not want percentages. Percentages are, well, they're just that. They're percentages, not probabilities. What is the probability that a student is neither a Facebook nor a Twitter? That means not in the Facebook circle and not in the Twitter circle. So what number do you see that's not in the Facebook circle and not in the Twitter circle? Well, that's going to be 15 over 150. So 1 out of 10 when you reduce, or you can write it as 0.1. Can't be either of those things. Now, 5 is an interesting question with this given. So Twitter, given they are a Facebook user. So the given limits to a smaller total. This will not be out of 150. The total is Facebook. So the total is Facebook. The total for Facebook we said was 127. So when I do this probability, it will be out of 127. Now within that 127, right, if I come back up here and I look, I want Twitter within that 127. I am only looking at these numbers. It's like the rest of the numbers don't count. So out of those numbers, the 93 and the 34 are also considered Twitter. So my probability is 34 divided by 127. Let's see if that reduces. It does not. And that equals, let's see, that equals 0.26. I would round that up to 8. I like to use 3 decimal places whenever I can. So my probability would be 0.268. Now, moving to the next section. Whole new question. You're hungry after school? It is after school, and I am hungry, so that's a true statement. We walk to Brewster's, sounds like a plan, to purchase a sundae. You have a choice of a cup, cone, sugar, or waffle. You have ice cream choices. They're limited that day for whatever reason. And then we have our toppings. You make one choice per category. Okay, so I think the easiest way to represent this scenario would be to draw a tree, right? We basically have 3 categories. We have like the holder, we have the ice cream, and we have the toppings. This is going to tell me from a tree diagram standpoint that I have 3 layers. You have the holders, then you'll move to your ice cream, then you'll move to your toppings. You have to choose them in that order. Well, I guess technically you don't have to say them in that order, but you're going to have to choose all 3 things. So that means you're going to build off of the end of each branch to get to the next possibility. So let's start with this. Your holders. You have cup, sugar cone, or waffle cone. That tells me I have 3 holder choices. I have cup, I have sugar cone, and I have waffle cone. So those are my first 3 choices. Now, off the end of each of these, I need to talk about ice cream. So ice cream, I have 2 options, right? So 3 options for your holders. I have 2 options for your ice cream. So off the end of each of these, I'm going to stick 2 ice cream options. And those are vanilla and chocolate. And then off the end of that, you've got your topping choices, and you have 3 options for toppings. You have sprinkles, you have hot fudge, and you have crushed cookies. So off the end of each of these, I've got to tack 1, 2, 3, 1, 2, 3, right? Because I have 3 options. And my trees are notoriously bad when I get out here, so just follow with me. Each one of these gets labeled with the same 3 groupings, right? You have sprinkles, you have hot fudge, and you have crushed cookies. All right. So if these are what I have, there's nothing in here that would indicate that anything weighs more than the other. There's nothing that's like 50% of the people get this and 10% of the people get this and blah, blah, blah. Like that would put weights on it. But for all intents and purposes here, everything is split evenly. So if you're going to talk about probabilities and you want to put them on here, like that first choice is 1 out of 3. The second choice is 1 out of 2, right? Everything's even. The third choice is also 1 out of 3. And this is where it's going to get hard to read what I'm doing. So just roll with me. They're all 1 out of 3. I'm just not going to label the other ones. That makes each branch on here, every single branch, and by branch I mean follow it to the end, every single branch is even. So you can just count up the number of options that you have here. You have, what, 18 options? There are 18 branches. So everything we talk about is like out of 18. Again, if things were weighted, it's not that simple. But things are all just considered equal, so we're talking out of 18. All right, let me come back over to the questions real quick. If you order a waffle cone sundae with vanilla ice cream and sprinkles, so you ordered that, what is the probability that the next person in line orders the exact same sundae? Well, it doesn't really matter what you ordered. Basically, it's just asking for the probability of waffle, vanilla, and sprinkles. So waffle cone and vanilla and sprinkles is one option. So 1 out of 18 would be our probability. Now, question 7, what's the probability that your best friend will order crushed cookies? Now notice crushed cookies, I'm not talking about all 3 choices. I'm talking about one choice only. So crushed cookies, well, we can think about it in just the grouping of the toppings. So you could think about it in just this grouping right here. And the answer is 1 out of 3. Or you could count up every branch that ends in CC. Every branch that ends in CC is 1, 2, 3, 4, 5. There are 6 branches that end in CC. So if you think of that as 6 out of the 18, well, at the end of the day, 6 out of 18 is still that 1/3. You're going to get the same answer. So both of them mean the same thing. It's just how you choose to view it. Do you want to just look at it as the little grouping, the little bundle of branches that's right there with just the toppings? Or do you want to look at it as the full length branches and you have to count up the total number? Both are valid ways to do that. Either way, you get 1/3 is the answer. Hopefully that helps a little. Now, the area model that's listed here that's already drawn for us is going to be used for number 8. Okay, we don't really know what they're asking other than just, is this a recommendation of a certain restaurant? So we're surveying 50 people and how many people would not recommend it. So this is the idea that we're going to find an expected value. But to do that, we kind of need to know probabilities. So I would love to find the probability based on this area model, but remember with area models, I can't really count up probabilities until I have equal sections. And if you look at it, they're definitely not equal. Now, this section right here is equal to this section and this section and this section and this section. Those are all equal, but they're not equal to the big ones. So what I'm going to do is I'm going to split the big ones. Now that's equal. And I'm going to split this and split this. Wherever you have a split, that block is just is counting as more of the same thing you had. So like I split that n down here, I split this n into 2 n's. It's not taking up more area, it just counts as more of an equal sized piece. So let's see. Okay, so how many pieces do I have here? I have 12 pieces. Right, 12 equal pieces. Now, how many pieces are no's and how many pieces are yeses? Let's see. So no's are 1, 2, 3, 4, 5, 6. 6 no's. Make sure that's 1, 2, 3, 4, 5, 6. 6 yeses. So the probability of a no Move out to the side here. So the probability of a no is 6 out of 12, or 1/2. The probability of a yes is the same thing. And so if I'm expecting not to recommend it, expecting means I'm going to take the probability and I'm going to multiply it by the repeats. So what that means is probability of no is 1/2 times I've asked 50 people. 1/2 times 50 people is I am expecting 25 no's. So I would say the answer to this is C. So that actually covered a couple of topics kind of in one question. Can you split up an area model into equal size pieces? Remember, you can't just count up until things are exactly the same size. Then you have to be able to calculate a probability and know that it's asking for the expected value, which is a multiplication times the number of times something was repeated. In this case, something was repeated 50 times because I asked 50 people the same question. All right, now we have an actual maze. So let's see if we remember how to do this actual maze. We'll figure it all out. Woo! Area model, all right. So if you'll remember, these blocks right here are always 12 down and 24 across. The first split that I have, looks like I have a choice of 3 things. That's going to be my rows. That first split is my rows. So I'm going to split my rows 1, 2, 3, 4, 1, 2, 3, 4. If you've got 12 up and down, and they've got to be 3 high, or 3 rows, words, rows. Each row is 4 tall. Now, take your top one. I'm going to change colors, y'all, and hopefully this will help a little bit. Let's take this top one. If I take the top row, every time I split, I'm going to split again. Now I split into 2 when I take this top row. So splitting into 2 means I split this entire top row into 2 pieces. It's 24 across, so 12. 1, 2, 3, 4, 5. That top one is no prize, and the bottom one, if I follow it, is a prize. All right, let me get you another color. Let's go with green for this middle one. Now, remember with these paths, we are only moving forward. If it looks like you're going to have to head backwards, we're not going to count it as a split. So this green one, while that looks like it should be a split right there, it only goes backwards, so I can't count it as a split. I just keep moving forward. That's a split. So that's split in 2. So right now that second row is split into 2, and follow it out. I get a prize, and I get no prize. So again, that bottom, that no prize one looks like it might split again, but that split would take it backwards. And so that's just not an option for us. All right, let's do this bottom one. I'm going to do the bottom one in gray. So this bottom one, it does split into 2. But then let's see, let me follow up the top. Ooh, if I follow the top, that splits again. So I'm going to have to split this one in half. We get the prize. We get no prize. Now, that bottom part of the bottom path follow it, and it splits again. So this splits in half as well, which will get us to no prize and a prize. This is the area model. Now, this is not something I can work with actual probability yet because things are different sizes. Like the top two rows, the top and the middle row, like they have the same size, but you look at the bottom and those are very clearly smaller. So the goal is they all have to be identically sized. This is where I draw in those extra lines. So let me draw in extra lines and let's do them in like maybe purple. So the extra lines, I think the easiest way to see this, because that middle line goes all the way down for all of them. What I need is I just need lines here. Now I typically do them with dashes instead of full lines. And I think of them as like both of those are P's and both of those are no P's. And both of those are P's and both of those are no P's. And there are my sections. If you need to do full line, you do full line to make it more obvious. That's perfectly fine. So for all intents and purposes, I would tell you that this area model had 12 sections. It does not actually have 12 sections. But for all intents and purposes, it has 12 sections, if we're going to talk about them as equal sizes. So out of those 12 sections, how many of them are not a prize? So let's count up no P's. There are 1, 2, 3, 4, 5, 6. So the probability of not winning a prize is 6 out of 12, or 1/2, or you can call it 0.5 if you want that decimal. So if 200 people go through the maze on a particular weekend, how many prizes should the farm expect to give away, right? How many prizes should the farm expect? So expect means take a probability and multiply it by repeats. So we want the probability of prizes. So how many prizes? That is again also 6. So we're going to take 6 out of 12 and we are going to multiply it by the number of people. The number of repeats, right? A person going through a maze would be a repeated action. It could be different people, but it's a repeated action. You're going through the maze. You're going through the maze. You're going through the maze. So basically that's 1/2 of 200. So 100 prizes to give away. And that's what we expect. Now this is because it's exactly 1/2 and 1/2 for the two. Just know it's not always going to be quite as easy as like, it's 100 prizes because just half of the things. This is 1/2 because it is physically 1/2 based off of our probabilities, not because I'm guessing. All right, let me go back to blue. All right, let's suppose you are playing a game, and I have no idea where those writings came from. We are playing a game that involves flipping a coin and rolling a die. So we're going to flip a coin, heads or tails, and we're going to roll a die, 1, 2, 3, 4, 5, 6. So the tree diagram has 2 actions. So the first action is coin, and the coin we either get heads or tails. Now this does say let's label probabilities. So if you have, I mean, and I think most of you know this, flipping a coin is 1/2 and 1/2 probability. And then your die, right, you're doing this, then you're doing the next one. So a die has 6 options. And each one of these has 6 options. I think I got all 6. So you could get a 1, a 2, a 3, a 4, a 5, a 6. The probability of each of those, because rolling a die, I hope you know, is not weighted either. So is 1 out of 6. Right? We're going to label all of these the same thing. And all of them are 1/6 probability. We finish labeling everything. So by the time you get out to the end of any branch, right, everything's equally weighted. It's very similar to what we did up top. There are 12 outcomes, and they are all equally weighted. So talk about it like we did up above. What is the probability you flip a head? Now, I only talk about head, so I only need to talk about those two pieces, right? Heads and tails. So the probability you're flipping heads is 1/2. What's the probability you roll a 1? So if I'm talking about rolling a 1, I'm only talking about that section. I didn't mention both things. So the probability I'm rolling a 1 is 1/6. What's the probability you flip a head and roll an even number? Now this is where you'd have to do both. Flip head and roll an even number. So we can count this up, right? If you look back up, and maybe I'll go back to a different color. We'll go to red here. If you go up to the top, you have to have heads. So I'm talking this branch for sure, this part of the branch. Roll an even number. Even numbers are 2, 4, 6. So that's really 3 branches meeting what I want. So 3 out of my 12 would be 1 out of 4 as a probability. Again, you can put it as a decimal if you would prefer. The other way to do this is to take each of these and multiply the probability. Flipping a head is 1/2. And means you are multiplying and an even. Now evens on this grouping right here, evens are 2, 4, 6. So 3 out of the 6 is my even probability. When you multiply that from a fraction standpoint, multiply straight across, so that becomes 1 times 3 on the top, 2 times 6 on the bottom. Here you see the 3 out of 12 show up, which is the same answer as 1 out of 4. Now, 16, what if we flipped the coin twice, then rolled the die? Okay, let me go back to blue. This tree's just going to get a little uglier. You're flipping the cone twice, right? The coin twice. So we have the first flip. We have the second flip. And then we have the roll. So off the end of each of these, got to put my 6. So if you count this up the same way we counted the last one, we have 24 outcomes. All right. If you're going to flip 2 heads, so that means heads and heads. Right? We can look at our diagram and we can say, well, we are only working with this right here. just the flipping of the coins part. That's 4 options, and one of them meets what I want. The other way to do this that I showed you a second ago, right? Heads would be 1/2, and 1/2, when you multiply 1/2 and 1/2, you get 1/4. What is the probability you would flip a head, then a tail? So this would be head and tail, and it sounds like the order matters here. You're going to flip a head the first time, and then you're going to flip a tail. Or you can see it on the tree as you flip a head and then a tail. So there's 1 out of the 4. Now, what is the probability you would flip both tails and roll an even number? So if you want to think about this as the multiplication piece, you can, or you can count, and I'll show you the counting in a second. But flip both tails. So this is tail and tail and even. All right, so tail is 1/2 and tail is 1/2 and even is 3 out of the 6 choices, which happens to be 1/2. You multiply straight across, you get 3 out of, that's 24, which is 1/8. If you're going to count it on the diagram, because this does talk about full branch lengths, right? We have to hit this tail, and we have to hit the next tail, but then the evens would be right here. So by the time you've gone down, I have 1, 2, 3 options, and there's my 3 out of 24. So if you were counting, 3 out of 24 meet the criteria, which happens to also be, of course, the 1/8. So you can either multiply those probabilities down the branch. That's one way to do it. Or you can just count, because these are all even. And I don't mean even as in even numbers. They're all evenly weighted, equally weighted, maybe a better word. All right, now here's another version of a tree that could be helpful for you. Brandon is playing a game at a carnival in which he tries to throw a ball through a small ring 3 times. If he makes a shot, he gets another chance. But if he doesn't, it sounds like he doesn't get another chance. So this means that my tree isn't going to be like symmetric. So we're going to draw, and it says tree or area. I like the idea of a tree here. So much easier than an area. So please don't do an area. You can, but please don't. All right, so here's the deal. We're playing a game. You get your first throw. Now for your first throw, he either gets it or he doesn't, right? So we'll call it a make or a miss. Now, if he makes it, he gets a second throw. If he doesn't make it, he doesn't get a second throw. So my make branch would get a second throw, but the miss branch does not. So make and miss. The same thing with the third throw. Your third throw, if you make the second one, you get a third one. But if you miss the second one, you don't get a third one. So the minute you miss, you're done. All right. So possible outcomes are this, right? You can make all 3, you can make 2, you can make 1, you can make 0. Those are the possible outcomes. Now, probabilities. This doesn't tell me anything about how often things happen. So if you are not given any information about how often or what percentage of the time something may happen, then you need to assume it's 50-50 in this situation. So 0.5 and 0.5 for everything. If you're told otherwise, if I say he makes it 30% of the time, you would put a 0.3 there and a 0.7 at the other location, right? The missing. Now, to make all 3, if he makes all 3, he wins $40. If he makes 2, he wins $20. But here's the thing, making 2 of them means he missed the third one. I get $20 with a miss. I get $10 making the first shot, but that means I missed the second shot. And then I think it's kind of clear that we make no money if we just miss the first one. So making all 3 is work your way out the branch by multiplication. 0.5 times 0.5 times 0.5. I believe that is 0.125. That he's going to make all 3. Making 2, again, follow the branch. All the way out to the end of the branch of making 2, that means he missed the third one. 0.5, 0.5, 0.5 is 0.125. Follow the branch for making 1, right? Making 1 is this branch. Making 3 is this one. Making 2 is this one. Follow that branch. It's 0.5 times 0.5. There isn't a third one. Because if I make 1, it means I missed the second one. So that is 0.25. And making 0 is just 0.5. Okay, so these are all of my probabilities that I have. Now, let's talk about what the question's asked. Okay, what's the probability that Brandon wins $10? Well, I already calculated it. It's 0.25. What is the probability that he makes $20? 0.125, and $40 is 0.125 as well. How many times should Brandon expect to win $40 if he plays the game 50 times? Right, here's that word expect. So I want the probability of 40, and I want to multiply that by the number of times that he's doing the thing, or the repeats is the way I say it. So the probability of 40 times the repeats. The probability of 40 is 0.125, and I'm going to multiply that by 50 because he's playing the game 50 times. Now this gives me a decimal that I encourage you to round off, because he's not ever going to win it 6.25 times, because you can't win part of a time. You either win or you don't. So I'm going to round this off to 6 times. Next question, what is the amount Brandon should expect to win if he plays the game once? Okay, so expect means, again, let's multiply probabilities times the amount we're going to win. It turns out I'm just going to add things together. So this is like almost like an average. It's like a weighted average is a better word to say that there. I would say this is very similar to a weighted average. So he expects to win $40 0.125 times. He expects to win $20 0.125 times. He expects to win $10 0.25 times. And he expects to win $0 0.5 times. I'm going to add all that up. So let's see, 40 times 0.125, that's a 5. 20 times 0.125 is a 2.5. 10 times 0.25 is a 2.5. And then 0 times is, of course, 0. That is $10 that he should expect to win. Now, that doesn't mean he's going to win the $10 every time. It just means on average, if he was to play it 1,000,000 times, he'd win $10 every time, or the average of $10 every time. So if we're asking you how many times, if you play the game once, you're going to use your probabilities times your amount of money, and you're going to add those together. Now, the only monkey wrench we can throw in here is if I tell you you had to pay for a ticket, you would subtract the ticket cost from the amount that you expect. So let's say you spent $3 on a ticket. This is all hypothetical. If you spent $3 on a ticket, you would expect to win $7 because you definitely spent 3. You would not win a full 10 because $3 is what you spent, and you would expect to win 7 of that 10 back. Very hypothetical situation. All right, we are almost done, guys. We have just a couple more problems. Casey's going to start college. We have to do a Venn diagram to model this information. Now, this information actually has 3 categories. There are males or females is one category, so gender. We have living on campus or not as a gender, or not as a gender, as a category. And then we have the type of computer as a category. So we have 2,200 total students. So let's Venn diagram this thing up. So I have 1, 2, 3 circles. So let's call this circle female. That means anything not in it would be male numbers. Let's call this on campus. Anything not in here would be not on campus. And let's talk about this one as being maybe a laptop. Anything not in this circle would be a desktop. So typically when I do 3 circles in particular, when I'm looking at a chart, I'm going to start in the innermost section. So the innermost section, middle section, this middle section is females on campus with a laptop, and we know that. That's 62 or 622. Females on campus with a laptop. Now, if I move out, I can just pick the next section to start talking about. So maybe we'll go here and talk about, sorry that just jumped. This section right here is females on campus, but not owning a laptop. So females on campus not owning a laptop would be the desktops, and that's 290. So let's move to another section. Okay, so this section right here, is females with a laptop, but not on campus. Now, that's where these two numbers are going to come in. We have females with a laptop, and then we have females with a laptop on campus. So females, laptop, not on campus is going to be 837 minus the 622. And that's 215. So I'm going to put that 215 in here. Now another section over here, this right here, that section is not female, so males with a laptop on campus. Males with a laptop on campus. So males with a laptop on campus is 600. That's straight up in the chart. Erase that. So males with a laptop on campus is 600. Now, as you can see, I've filled in 4 numbers, 4 sections. I have 4 more sections to go. All right, now let's work our way maybe out here. Let's just talk about this part. This part is females, not laptop, and not, denote that the same, not laptop and not on campus. So this is females, not laptop means desktop, and not on campus. Okay, so females desktop not on campus is right in here. So we're going to take that 314 and minus the 290 is 24. So 24 females do not have a laptop and do not live on campus. So let me move on. Ooh, 3 circles are kind of brutal. All right. That section right there is not females, so males. That is not a laptop, and it is, though, on campus. So males, not a laptop. So males, not a laptop on campus. So males, not a laptop on campus is 214. That is right here. So this section is 214. Down here. Whew, guys, we're getting there, I promise. This section down here is males because it's not females. This is a laptop, but it is not on campus. So males with a laptop that are not on campus. Males, find my male numbers, with a laptop, so I'm under laptop, not on campus. All right, so this is going to be that 756 minus 600. So I'm going to put a 156 right there. The last section is this outside number. And the outside number is, well, it would be males, because it's not females. It would be what? It would be males. It would be not a laptop. And it would be not on campus. So males without a laptop that are not on campus, not a laptop meaning desktop, on campus, not on campus. Okay, so 293 minus the 214 is 79. So the outer portion is 79. Ooh, a 3 circle, man. It's a 3 circle. All right, so let's find the probability that a male owns a computer. Oy. All right, male. So male over the total would be how I find this. My total, we said, is 2,200. That's up in the directions. So a male owns a computer. Okay, male own a computer. So here are my males. Right here. I don't need to worry about the row below it because those are males and campus. So just a male. Males would be 756 plus 293. That is 1,049 out of 2,200. You can reduce that if at all possible, or you can just divide and get your decimals. I would say 0.477. Now find the probability that a female owns a laptop given she lives on campus. So given lives on campus is my total. Now this I think will be easier if we look at it with a different color. Let's look at it with, what color will really stand out here? We'll just do red. Given she lives on campus, the on-campus bubble is a full bubble. That's my total. So my total is the 290 plus 622 plus 600 plus 214. That's the number that live on campus, and it is 1726. So my denominator is 1726. Now this is probability of a female owning a laptop. So female owning a laptop is a location. Female owning a laptop is right here. Now it's only within the on-campus circle. So I would say that 622 out of 1726. And that is 0.3603, so just 0.360. That's tough, y'all. That 3 circle one, that is not an easy one to deal with. My hint to you is I didn't put one of those on the test. At least not required. Okay, so it's not required if I have to do that. Now, creating a Venn diagram for these scenarios, we just have to read, these look like they're 2 circle Venn diagrams. So yeah, 28. Read it. 128 students in the sophomore class. 85 of them have a brother. 23 have both a brother and a sister. 5 have neither a brother nor a sister. This is definitely a two-circle Venn diagram. So we have 128. This is the total for the diagram. 85 is a brother circle. So it's the whole circle. 23 have both a brother and a sister. That's a section. So we have brother, we have sister. 23 have a brother and a sister. 5 have neither a brother nor a sister. That's outside. Now, 85 of them have a brother. That's a circle, right? Remember, that's a circle. So for this section right in here, I'm going to use 85 minus that 23, because the circle is 85. So this section is 62. We also know that we have sister numbers, the grand total of the whole thing. So we'll put another little symbol. The grand total of the whole thing is 128. So we'll do 128 minus the 62 minus the 23 minus the 5. We get 38, so this section is 38. And we're not doing any probabilities here, we're just drawing the diagram to make sure we can draw those diagrams. All right, 29, same idea. Last question we have to go over. I know it's been long, guys. Thank you for sticking with me. So on 29, we have 554 seniors. 65 play in the band, 482 are in clubs, and 65 are involved in neither. Okay, so we have band and we have clubs as my numbers, right? 554 is the total for everything. 65 is a circle for the band. 482 is also a circle. And 65 are involved in neither. So 65 are involved in neither. And you may be like, well, how am I going to get this overlap? Well, again, we have a total of 554. So to find the overlap, I am going to say 65 plus 65 plus 482. Those are my two circles. Right, that's B and that's C is a circle. That's going to equal some value. That equals 612. Now I told you though that the total is 554 total. So that's too big. The too big is the overlap. I'm not saying 612 is the overlap. The too big amount. It's too big by how much? So subtract 554. And you get an overlap of 58. So there are 58 too many in this diagram. That must mean that 58 people were counted twice. Now we can go back and do the exact same thing to get the full B that we did the last time. So the exclamation point would be take that B circle, band of 65, minus the 58. You get 7, so there's 7 out here. And then I'm just putting these little symbols, by the way, so you can find the calculation. So my little smiley face would be 482 minus the 58. And that's going to be 424. So I put a 424 here. So when it comes to Venn diagrams, these are kind of the two ways you would find it. Either you have enough that when you add it together, it's too small, and whatever you need that's lacking would get your last piece. Or you have way too much. And if you have too much, then that tells you the overlap. So when you add it up, it's way too big. And adding it up and getting way too big means there's your overlap and you can start subtracting away. Those are kind of your two options for how to draw two circle Venn diagrams. Now, I hope that this helped. I hope you were able to find what you were looking for in here. And good luck studying for this test. Let your teacher know if you have other questions. Thanks, guys.